Hello everyone, my name is Yongjin Fu. In this presentation, we introduce SVoice, an application system for silent speech, which is designed for voice communication by reconstructing speech from silent speaking gestures based on acoustic sensing. There are some application scenarios for SVoice. First, as a complement to voice technology, SVoice allows people to call quietly in public without disturbing others, and it also avoids leakage of the call content. Secondly, SVoice can also help some acquired aphasia regain the ability to speak. Some previous works consider using wearable sensors to capture articulatory gestures such as EMG and EEG. However, this requires prolonged contact and may lead to allergic reactions. Other works use vision-based technology, but the camera cannot work in low-light conditions and raise privacy concerns. We construct an inaudible solar system using microphones and speakers on the commercial devices to capture silent gestures for speech reconstruction. Compared to other sensing technologies, our system maintains the advantage of non-invasive, ubiquitous, and can work in low-light conditions. First, we introduce how to sense the gesture with the inaudible acoustic signal. Since the human speaking movement is fast and subtle, a sufficient fine-grained signal design is required to capture the gestures. Considering the sensing vacuum of the symbol-based approach, we choose continuous wave as the transmitted signals. Then, we use coherent demodulation to get the phase and magnitude. In addition, we use gradients and multiple subcarriers to reduce the effects of static interference and multiple effects acoustic. Secondly, we need to reconstruct speech from ultrasonic. Reconstructing high-dimensional speech from low-dimensional ultrasound is very challenging, just as we cannot infer what a person is saying from a picture. Therefore, we design neural networks to exploit the rich contextual information of speech. We take MFCC as intermediate prediction and use the two-stream structure to extract features from phase and magnitude gradients, respectively, and utilize a multi-head attention mechanism to extract multi-channel contextual information. The audible speech is finally reconstructed from the MFCC by a vocoder. Thirdly, the mapping between speech and gestures is very complex. There is a phonal-level overlap in speech due to different contexts, which degrades the performance of the system on synthesis. In practice, the overhead of collecting a dataset containing enough synthesis is unavoidable. Therefore, inspired by back translation in machine translation, we explore rich synthesis structures from wild audios and generate virtual gestures. To improve the quality of the generated data, we use SIGAN and Cruise Model Similarity Discrimination Network to reduce noise in the generated data. Fourth, since speech is user-dependent, the user adaptation of our system relies on paired data from new users, which cannot be collected from acquired aphasia. To address this challenge, we use the audio in the user database as a label, which can be paired with the ultrasound signals collected from the new user, thereby eliminating the reliance on the label for fine-tuning. However, due to the speaker differences, the speech labels and ultrasound signals are not aligned in the time domain. We use DTW to construct a novel loss function to reduce the effect of time wrapping and find the best matching audio in the user database. Our experimental data are collected by users with smartphones holding in their hands, including more than 30,000 data pairs. The main evaluation metric is the character error rate. The experimental result shows that the intonation information is preserved in the reconstructed speech, which is represented by its recovery of sentence-level pitch changes. Then, we compared the performance of SVoice in vocalization and silence, and we noticed that despite a slight loss in performance due to the auditory feedback, the overall CER remains low. We also evaluate the impact of virtual gesture generation, and the experimental result shows that the data generated by SVoice is more effective, which can maintain a low CER on unseen sentences, but there is a limit on the number of wild audios. In addition, we evaluate the effectiveness of our user adaptation mechanism, and the results show that SVoice can fine-tune the model using unlabeled data. Finally, we make a conclusion. First, SVoice designs an end-to-end silent speech interface that reconstructs audible speech using ultrasound signals reflected by articulatory gestures in silence. Second, SVoice presents a cross-modal data augmentation mechanism that can generate virtual ultrasound from the wild audio. Third, SVoice proposes a user adaptation technique that utilizes a small amount of unlabeled ultrasound data to fine-tune the model for different users. Thanks for your listening.